In this presentation, what we'll do, I'll not go into the deep learning and all. Okay, we'll just try to understand the concept of speech and how a simple filter can be used to analyze the speech signal for speech parameterization and other applications. Okay, so we'll start from the third semester itself. Okay, third semester signal system, and from there I will convert a simple integrator to a filter. Okay, integrator is also a filter, but I will make it a adaptive filter for top applications like ASR, KWS, and different hardware implementations. Okay, we'll focus on this. Is all total a fundamental concept. Okay, we used to read it in our third semester and so. So, sir, 8 minutes. Okay. So in this presentation, what we'll do, we'll just first any fundamental thing if we'll do. First, we have to understand the physics behind this. Then we'll discuss these filters and all, and how we'll parameterize speech data using these filters. Okay, in a speech signal, if I put a mathematical model for a human speech production system, there are two things involved. One is excitation. Any output, if you observe, there should be a system and there should be input to that system. Here the input is the air pressure, okay, and the system is our vocal tract, starting from larynx to mouth. Okay, so this is a filter we use to make different configuration of the vocal tract to give a resonant and anti-resonant structure to the airflow. Okay, so finally the speech is produced. The excitation in speech, there are two type of excitation. One is periodic excitation. This excitation come into picture when our vocal fold vibrate. So it will vibrate when there is a rush of air pressure on to the vocal fold. Okay, so there is a vibration. So it will create a impulse like excitation. That is periodic impulse. It is not a equal height, but it is that amplitude and periodicity. Everything will depend. So depending on the vocal tract mass, vocal fold mass, and the vocal tract length, the speech will get a different resonance and anti-resonance structure. And there is another type of excitation. This is a random noise. Just like if I say those envoy sound like sa, ka, kha, that there is no vibration. But if I say the vowel sound in it, all those things, there is a impulse like excitation. So this excitation, this excitation is unique for a speaker, depending on the vocal tract, the vocal fold mass, the way they used to excite. This is one feature, and another feature is vocal tract system, that is resonance and anti-resonance. So for different sound unit, we are giving different type of resonance. Suppose the formant structure, the resonant peaks for a vowel sound unit is different from the other sound unit. Similarly, for a person, his or her way to make a resonance structure is different from the others. So mostly we used to this machine learning, all those things, we used to capture this vocal tract information. That means this resonance anti-resonance structure that we used to model for development of speech application systems. So since it is a filter, so we know this in our third semester, if there is a filter, there is a input to this filter, the output is convolution of these two signals, excitation and the vocal tract response. Okay. So when there is a excitation, let's say impulse like excitation, if I take its frequency domain response, it is also impulse. Okay, so when there is a random noise, the spectrum will be flat. We know power spectral density of white noise is flat because it is an uncorrelated signal. Okay, so this presentation will try to see there are applications where, let's say, I'm developing a ASR system on adult data. Let's say that system will be used by a child or a elderly age persons. So at that time, this excitation plays a great role it will not allow the system to operate properly. So we have to normalize it. Okay. Suppose if you are doing a speaker recognition system, that time this excitation is a good feature. We have to use it. Suppose we are doing this segmentation of the speech signal, this excitation plays a role. Okay. So this is the concept. If you look into the speech signal, as I told, the speech signal, there are different sound unit. When there is a resonant structure, this is vowel. There is a open mouth, is open widely, and there is a periodic excitation. You can observe this is a periodic excitation here in voiced sound unit. Okay, there are vowels, semi-vowels, okay, and diphthong. Diphthong means if two vowels will be come closer, okay, there is no time for transition from one vowel to other vowel. So we'll take these two vowel as a consecutive unit, that is one phoneme, that is called a diphthong. Okay, and if you look into the unvoiced cow, as I told, there is no periodic excitation. Okay, so this is excited by a random noise type of thing. Okay. So whenever we'll do ASR means suppose they given a speech, I have to translate to a text. So every sound unit I have to have a corresponding text. So we'll concatenate those phones or sound to make the words, and we'll concatenate the words to from a sentence and all, we following the grammar rule of the language and all. So this is the objective. So in a speech signal, if you see in time domain, the duration of sound units, the amplitude, the frequency, all those things are observed. If you go to the frequency domain of these sound units, we can see, since in frequency domain, in time domain, it is convolution. In frequency domain, if you apply Fourier transform, let's say, so the convolution become a multiplication. So there is a impulse train and multiplied with a slow varying resonance structure. Resonance structure means this format. If I take, when I develop a ASR, I should normalize these things. It will be a spectral envelope things I have to model. This envelope, it will be unique for a speaker and unique for every sound unit. You can observe there is a pitch effect. Okay, this pitch effect is a speaker specific factor. If it is added, suppose as I told, I develop for a particular type of gender, like let's say Google Siri or Amazon Alexa, all those things. It is the train on a adult voice. If my kid will try to operate on those things, it will not work due to this pitch variation. And there is another thing also, speaking rate. So how much time I used to speak, all those things. Okay, this is a decaying thing. Okay, there is a resonance structure, and in speech we observe 4 to 5 formats. On contrary, if you go to this unvoiced sound unit, we will see the rising spectrum, and this excitation effect is, I have taken a voice consonant like ja, that is some excitation, so it is observing. But if you take sa, that is simply a rush, there is no such thing. The format structure will not be observed in this thing. Okay, so my objective is I have to use a simple filter, fundamental things. Okay, so to develop the speech recognition systems. As you know, in speech there are many information, the speaker information, the speech, the message, what I'm trying to speak, that is the speech recognition. Or if I search for some keywords, just like we are searching this Lata Mangeshkar song, or assembly result of Tamil Nadu, that means some keywords we are searching. We are not searching for a entire utterance. But if what I'm saying, if you write it, it is a speech recognition, word to word conversation. There are language identification, language, different languages, which language. So this language translation mission and all. Speaker recognition, who is speaking, gender, health, different health condition also we can observe from the speech, like Parkinson's disease, dementia, this dyslexia, all those things we can detect from the speech. We can detect in emotion condition, and all those things are embedded in the speech. And when we work with the computer, the sensor also play a sensor, and the environment, the background where we are recording, giving the speech, that create a challenge. Okay, so that is another domain of research, that is the speech enhancement. Okay. So whenever I am, suppose let's say I am developing a speech recognition system, I have to normalize all the other things. That means language, who is speaking. It is not, suppose Google, this Amazon Alaska or the Google Siri, it is immaterial who is speaking, it is working. That means that speaker factor is normalized. Okay, but the language factor is there. So if I develop such a thing, let's say Indian languages, suppose I have developed a system on Tamil language, it will not work for Oriya. So that thing I have to normalize somewhere. Okay, so gender, health, everything, it should be normalized. So that is the main challenge in speech recognition. It is a different type of data. Okay, it contains many, it is rich of information. So when there is a rich of information, so when I am developing one system, that other information create a problem, hurdle for that. It is not like image, all those things. There is many information. Okay. So if I develop any applications, there are different modules in that. One is how will you represent the speech. That means front end speech parameterization, feature extraction, we used to say. Then how will normalize those features to separate, to suppress the redundant information. Just like I'm developing a speaker recognition system, I have to normalize speech information, language information, all those things. Then we'll go to the statistical modeling. Statistical modeling you can do to the conventional approaches, or you can approach a deep learning approach. You are say computer science background people, so you might be using deep learning methods. Okay, but there also you have to give a parameter input. I have to give. Okay, and nowadays people are saying end-to-end system. End-to-end system, there is a speech and the neural network itself, which is extracting feature, or we can use some pre-trained models. Okay, so pre-trained model also the filtering concept and there, but here whatever we are doing in signal processing way, we are designing this filter and all. In neural network, the neural network itself it is used to design the filter depending on the data. So if I extract the feature from the speech, I can extract the feature in time domain. This means on the signal itself in temporal domain, or I can take the data to the spectral domain. That means frequency translation, wavelet, or EMD, BMD, whatever may be. We can go to the frequency domain and I will do analysis in the frequency domain. That is one approach. And we can use spectro-temporal representation, time frequency representation. Just in CNN, all those architectures, you see there is an image form of the speech. These architectures are initially designed for image processing, video processing. Then we can apply the speech as an image, just like spectrogram, male spectrogram. Even wavelet will decompose in different frequency band. We can use the different filtering to decompose the speech into different band. And as I told, there is another approach. Okay, the pre-trained model. Pre-trained model means here we are using a small footprint systems. That means limited data. In pre-trained nowadays, people are saying data is the core. So if I have some, let's say 1 lakh hour of data, and I have a machine to train it like Google, so I can do it. I can use a pre-trained. I can develop a pre-trained model. Okay. Suppose there are pre-trained models just like we'll say web to vector, or bot embedding, or we can say WebLM. All those are pre-trained models. Okay, this is a black box. We are giving the speech. It will give some parameter, some dimension. It is a matrix. It will give the matrix. Okay, because it is trained on a huge data, so the neural network learns the speech parameter. But if I say I don't have such a model or computation, suppose I will develop a data where I can use this Tamil, all those things, Oriya. So I don't have a pre-trained model for that. Okay. Either way, I can retrain those models. Okay, by removing some layers, or otherwise I can use my concept. Okay. So we'll start from this very basic concept. We know the integration. Integration means integration. Its other name is accumulator. That means we studied in our +2 level thing. If I integrate something, that means I have some data. I'm adding all those data one by one. If you look into this integration, it is a digital data, because once I work with the computer, it is a digital data. It is not analog data. So we have a digital data, digital form of the speech. Will accumulate. Accumulate means this is the equation. That means from infinity, some point to some point, we will adding this data. Okay, that means minus infinity to n we are adding. If I just rearrange this equation, I can write y n minus 1. Okay, y n minus 1, if I write, it will be minus infinity to n minus 1. That means I can, in a recursion, I can write it. It is yn is equal to yn minus 1 plus x. Just I will arrange this equation. Okay, if you know this G transform or frequency transform, if it, frequency domain, if I go, this is a delay, one delay. That means I have a output. I'm taking the feedback of that output. With you, feedback means one delay, and I'm giving the current input. This equation means I have something. I'm adding one data and getting the output in a recursion. Okay, I need not to add, keep on adding every time. I have some data, I will add it. Okay, so one delay means it in G transform, it will be G to the minus 1, one delay. So if I'll take arrange this transfer function means output by input, output by yj xg, it is equal to 1 by 1 minus g inverse. This is a, you can see the, if I'll solve this equation, that is a numerator and that is a denominator. Numerator represent the poles. Okay, these poles, the numerator represent the zeros, the denominator represent the poles. These poles are important for human perception because these poles give rise to resonance and anti-resonance structure in the spectrum. But if you look into this filter, this is, if you know the stability and all, because I'm keep on adding, at some time it will be overflow. Suppose I have a box, I'm every time I'm dropping 1 rupees, 1 rupees, at some other day it will be full. So what I have to do? I have to clear that thing. So this is a filter. If you know this G transform under that unit circle, okay, it is on the unit circle. On the unit circle, it is unstable, marginally stable filter. So I have to, for any stable realization, I have to make it stable for any real-time application. So I can do it. What I'll do? Suppose, let's say with a simple example, suppose daily I am keeping, let's say 1,000 rupees, 1,000 rupees, 1,000 rupees. So it will be fill fast. So if I view today 1,000 rupees, after 10 years it may be equivalent to 1 rupees. Okay, so I can normalize this thing. Okay, this I'll introduce a that is a constant. If I'll introduce here, okay, what I'll do, I'll not add xg, I'll multiply something, some small number and add it. It will give, represent the data itself. Okay, so then I'll say it is a yn minus 1, where a is less than 1 and it is a real constant. And if I'll put a is equal to 1, if I'll solve this equation, I'll have g is equal to 1. But here if I'll solve it, g is equal to a is something less than 1. So it will bring the stability to the filter. Okay. So now it is a single pole filter, because single pole filter means only I have one root. It is a IR filter. Okay, I have only pole. It is a IR filter. There are filter are two types. One is FIR and IR. Okay, it is not like that. IR filter is always unstable. Okay, IR filter, it requires less hardware because only I have one multiplier and one delay. But if I implement such a filter with FIR, I may need some 100 multipliers and all. It will increase my computational complexity. Only requirement is the stability. So I can bring the stability by keeping a less than 1. So now if I solve it, this is my thing, and this is a single pole filter. Why I am saying single pole filter? Because I have only one root. Okay, it is IR filter. So now the accumulation, now I will convert to this filter. This is a bandpass filter. Okay, so I can convert this filter to a zero frequency filter. Zero frequency filter means it will capture the data around very low frequency. So therefore we are saying it is a zero frequency. Zero frequency means if I accumulate multiple times, so it will rise fast and it will remove. Accumulation means suppose I have a data 9.5, 9.2, 8.8, 8.9, these small variations. If I add it, so it will, the small variation will be removed. Only I have a big data. So that small fluctuations will be, the filtering means there are two type of things. One is small fluctuations. This is at the high frequency. Small values vary varies with a high speed, and a larger value, okay, it is varying with a small rate. Okay, just like if I say stock market every 5 minutes it is varying, but if you variation of a stock over the month, if you see, the variation will be some small larger variations. Okay, in Delhi it may be varied in 10 rupees, 5 rupees, 8 rupees, 2 rupees, but if you look over a 1 month period, the variation may be 1,000 rupees, but that variation is not fluctuating much. Okay, so that is the thing. So what I'll do, so I have to first remove the DC. DC means this recurring offset is there in the data. So if I'll remove it, so I will first data minus previous data. So whatever the constant value, that will be removed out, and it is, you can say it is also a high pass filter. Okay, it is a high pass filter because if I take a differentiation, integrator is a low pass filter, so differentiator is obviously a high pass filter. Okay, so what I'll do, I'll just concatenate such a 4 filters to make a filter order of 4. You can see here it is order of 4. There are 4 k values. If I have not solved it, you can solve it 1 by 1 minus G inverse into 1 by 1 minus G inverse into 1 minus A G inverse to the power 4. We can see if you solve it, you will get 4 roots of this equation. A is equal to 4, A2 is equal to this. This is a, you can see if you know DSP, it is a 4th order filter. Okay, so we'll get this thing. Okay, if I accumulate 4 times, it will be sharply rise. In, as I told in speech, if I have a data, let's say 10, 10.5, 5, 10.5, 11, like that. If I subtract this over a block of data, then whatever the variation in the local region, it will come into picture. Okay, we'll see that is the detrending filter. It is also a filter. Okay, so if we have a, let's say, we'll see through a graph, we have a speech. Okay, it is a periodic speech. Okay, so this is a voiced region. Okay, so if I accumulate it, keep on accumulating, you see it is 1 here, but it is 10 to the power 6. What a huge value. Therefore, I am saying it is unstable filter because I have to store this data through a memory. So I don't have such memory to store this data. But if I take a period and subtract, there is a variation in this data, but it is not observable because if I'll say I have 1 crore rupees, you have 1 crore 1 rupees, 1 crore 2 rupees, it is not observing. But if I subtract 1 crore, so 1, 2, 3, it will be displayed because that 1, 2 variation will be there. But in comparison to 1 crore, 1 rupees is not observable. Okay, so if I take a frame of data, that means if you come back to this thing, this first slide itself, we can see there is a periodic extension. If I subtract the data for this period, so whatever these variations will be come into picture. Okay, so that's it we are doing. Okay, so if you do this thing, so what we'll do, I'll subtract it. This paper is proposed by method Professor B. Agrana and his group in 2008. Okay, so if you'll show it is a breakthrough method. Okay, we can see this is a slow varying signal. That means it is a like a single monotone frequency, monotone signal. Monotone means only one frequency component, that around the 0. Okay, because as I told, the impulse have a Fourier transform. It is low, but vowel, the consonant, it is flat. Okay, so high frequency, low frequency are correspond to the voice. So if I take this 0 crossing point, these are nothing. This is at the glottal closure instance. These glottal closure instance are useful in many applications like speech synthesis and all. Just like हम लोग बोलते हैं ना जो AI में we are changing the voice tone, all those things, because they used to change this glottal closure instance. If I place this glottal closure very closer, that pitch will be increased. Okay, so this glottal closure instance. So this is one filter. We can see the simple accumulator we have converted to a very powerful filter. Okay, there are many things, applications we can see on this filter. Okay? So next, okay, so what I see, there is a filter we have designed. That filter, low pass single pole filter, its cutoff is around the zero frequency. Suppose I want to design a band pass filter. Band pass filter, what we used to do? We used to pushing through different filters, okay, with different bandwidth and all. I can use this filter, this single pole filter, 1 by 1 minus G inverse. This is a first order filter that I can use to analyze the frequency. Here, what we have analyzed? We have analyzed only the frequency around the zero. Now, speech frequency, we used to modulate different frequency differently. So, the way I am modulating the 10 kilohertz frequency, 5 kilohertz frequency, or some 8 kilohertz frequency, it is different for me. If you will modulate different frequencies differently. So how will get it those frequencies? I have to find out those frequencies. What is the amplitude variation for those frequency bands? Okay, we know, if you know this DSP and all, in signal system, there is a frequency shifting property of the Fourier transform. If I multiply e to the power j omega t, it will shift the frequency, angular frequency, omega to omega minus omega naught. So what we will do? We will use that concept to bring this single low pass filter, single pole filter, to make a band pass filter. That means it will analyze the different frequency. That means if I apply the Fourier transform and all, that is the drawback of Fourier transform, because it will analyze the complete data. To solve for a speech applications, we have used to do short time Fourier analysis. Short time Fourier over 20 milliseconds. Even the 20 millisecond, that windowing effect and all there. So we have to remove that effect. So we can apply this filter to find out the instantaneous frequency. Instantaneous frequency means at every instant how the frequency will vary. But if I apply this short time Fourier transform, all those things, as I told in male spectrogram or spectrogram, that windowing effect is there. So that to normalize, I think we can use the instantaneous frequency. Instantaneous frequency, if I do, what I'll see, I'll multiply e to the power j omega. Okay, this is the basic property I have discussed, that if I'll multiply e to the power j omega t with the data, it will obviously shift the frequency. That the filter I have designed, that is a unit circle, I have designed at pi, then I am multiplying omega, it will shifting my frequency. So first I will say, I'll have frequency FM maximum frequency I'll keep, then I'll shift some frequency by multiplying omega, it will next frequency. Even I can analyze each and every frequency being at each and every time instant. That is the beauty of this thing. This is the time frequency representation. So what we'll do, we'll apply e to the power j omega t, multiply with the data e to the j omega t. That d omega t will decide which frequency I am trying to analyze. Suppose I am analyzing 200 hertz or 2 kilohertz or 5 kilohertz. That decides this omega t. Omega t I will multiply and xk, and I will pass to that filter. That is simple thing, as much simple as that. Instead of passing xk, if I pass xk itself, I'll get only one frequency. If I multiply e to the power j omega k, I'll get multiple frequencies. Okay, so pass through this frequency. Okay, this is the same equation. I have seen yk, here d term is there because of different frequency beams I have to represent, therefore I'm writing d. So same equation, a y n minus k xk, same equation, and whatever the amplitude I'll get, this is a complex envelope, so I have to take this magnitude. When, if you know the Fourier transform model, if you apply Fourier transform, I'll get a complex number. I have to analyze the magnitude spectrum because I want to get the spectrum format and resonance, anti-resonance. Okay, so I have to take the magnitude. Here also I am taking magnitude. Okay, magnitude a plus jb, so a square plus b square root over. If I try to analyze phase, so I have to find out this phase. Okay, tan inverse b by a. Okay, so there is we'll see how this filter works. This is a speech signal. Okay, there are different frequencies. If I apply this filter, I get a time frequency representation. This is my time axis. This is my frequency axis. At which time? Okay, what are the frequency component is there. Okay. So now, as I told, if you want to apply to a deep learning architecture, okay, you should have a time frequency representation, a matrix of data. So you will get a matrix of data. Okay. You can see, depending on the sound unit and all, this amplitude, which frequency, what sound unit, who is speaking, what is the emotion, many things you can do it. Even this original paper, it was designed to get the speech detection in case of noise. Noise means what they argued that at every frequency, that variation and all, depending on noise, it will not, it cannot suppress the speech data. So that variation will be different from the where the speech is present. Okay. So this is the output. So we have got a time frequency representation. Okay, so we understood this very simple filter what we have studied in our third semester or second semester. Okay, so that can be used for a big application. Okay, it is now ready for application. So as I told, the one question is there, that is an unstable filter, because this is keep on growing. So I can bring make a stability to that thing by a simple adjustment. Okay, we have done this adjustment. Okay, so what we'll do, if you look into this, as I told, I'm not discussing all those things. Okay, so what do we have? As I told, I have 4 cascading of this thing and multiplying. Okay, 4 times I'm multiplying, then 4 times I'm subtracting. Okay, once I'll accumulate, then small variation by retraining we are doing. What we have done, we have solved this equation. Why not I concatenate? Once I'll accumulate, then I'll subtract. Then once I'll accumulate, this is the kth order. That means I have accumulated, then this kth point, 10 numbers I have accumulated, then I will subtract what is the value at the 10th and what is my first value. That is the slope of the data. Because I have a data, I'm accumulating, it is going. So what is the slope? Y2 minus Y1 divided by X2 minus X1. That we know from our standard mathematics. So that means this is my slope. If I'll solve it, Yn minus Yn plus K. After K point, I'm taking the value and subtracting. Then I'm next K point, okay, average magnitude dynamics, that we used to say. This is the design of the filter. We have just solved it. Instead of detrender, we have used for kth order differentiator. Okay, so now I will do this thing. I'll take this. It is a cascade. I can arrange this. Cascade means H1, H2, H3. I can H1 के बाद H2, then H3. I can use it. So if I solve it, so I will block this. Just take this thing to this thing, this thing to this thing. Okay, this after that, that after that. Okay, so if I do this, this equation will be like this. This equation will be simplified, because in that case, what we have done to xn plus 1. That means what is the past value that I subtract. So it will never increase. मैं क्या कर रहा हूँ? What I am doing? I have a box. Daily I am adding 100 rupees, 100 rupees, 100 rupees. After 10 days, I am taking out 100 rupees. Next, I am adding. After next day, I am removing what I have kept before 7 days. So it will never fill. What it will preserve? It will only preserve the data for 10 days. 1000 रुपया से कभी भी मेरा बॉक्स में ज्यादा नहीं होगा. Because every time I am adding, after 10 days, I am taking 100 rupees. Next day, what I have kept in the second day, I have taken. So next day, what I have kept in the third day, I have taken. So it will only contains the 100 rupees. So 1000 rupees. It will never. What I am adding and I am spending. जैसे हमारा सैलरी मिलता है, हम 2 लाख मिला, 1 लाख खर्चा कर दिया. So बचा कितना? 1 लाख. अगर कुछ खर्चा नहीं करेगा तो ओवरफ्लो होगी, 100,000 करोड़ हो जाएगा. वो तो होगा ही नहीं कोई. So that concept we have used. Okay, and we have applied. This is a stable filter, that instability we have removed. This is the data. Okay, this process step by step, and we have got this glottal closure instant. Okay, so Similarly, we have compared with the original thing implementation and this. Okay, it is giving same thing. And you can see, as I told, the frequency response, it is around 0 only. It is a very sharp filter. It is, therefore, it is called as a resonator. It is not a filter, it is a resonator because it is a sharp peak, then it is falling. Okay. These two filters are almost similar, but this one is unstable. I cannot, unstable for software implementation, instability is not a issue. I can use, I have a computer, I can use it. I have a server, I can use it. But when I go to hardware, a chip, then that creates a problem because it is requires a huge memory. Okay, so this is the thing. We can see this is the speech, this is the filter output signal, as I told, and this is the glottal closure distance. Okay, so hardware implementation, if you see the stable filter, all those things. Yeah, as I discuss, this is a multiplier, 128 multiplier for such a filter, a fair filter, if stability address. Okay, because here it is reduced drastically. Okay, hardware, and this is a very simple filter. Okay, we have patented it and we have published on paper. Okay. So this is filter, one application we have seen. Now I will discuss multiple applications. Okay. So just I will take a 1 minute break. 1 minute. One fellow is there. Yeah, Aditya, call him. Okay, so this is one application. Now we'll see that is the sound is the house. So how we can detect the vowel using this filter. That means this slope, if I accumulate, if there is a sudden change, that accumulate that thing, suppose every time I'm adding 100 rupees, one day I added 2000 rupees. So there is a sudden jump. In signal, speech signal, when there is a vowel start, there is a sudden jump in the signal amplitude. So that point we can detect through this first order filter. What we'll do? We'll accumulate it. And after some time, because for hardware implementation and all, we can address the stability in another way. I'll add it somewhere, then I'll reset it to 0. Means I have kept 100 rupees for 1 month, then after the end of month, I have purchased one shirt. Then that box is empty. So what we'll do? We'll do this thing. This is the same filter design. Okay, non-local slope difference. What we'll do? I'll just going to this data. Okay, so transition point, if I do transition point means what I have to do? I have some data. Transition means if I pass through a Gaussian differentiator, it will detect the Gaussian differentiator. Gaussian function will be something like this, a bell-shaped curve. If I take the first order difference, it will be rising, then it is falling. Okay, it is Gabor filter type of thing. Okay, so what I'll do? Will this is the function. If I take its difference, it will be look like this curve. Okay, so there is a non-local difference. What I told, I'll keep on adding. When I'll found there is no signal at all, then I'll vacate it. I'll make it 0. Then I will again keep on adding. So you can see this is the transition point. That is the starting point of a sound unit. This is also important task. You can use in front end of the speech processing, all those things. If someone give me the boundary, okay, we can do it. Okay, so we have this data. Then what we have done? Okay, we have this some engineering solution. We have done this to bring this transition high. We have used this nonlinear mapping through exponential function, or you can apply the log. Okay, neural network that we used to use this nonlinear functions. So here we have used nonlinear function. So there is a rise. So what I'll do? I'll track this point and did mark these sound units and separate from the data. There are different applications where these vowel sound units are important. Suppose development of application like speaker recognition, all those things in presence of noise. When there is a noise, since this magnitude is more, it will be less affected. Okay, So these are the stable regions. So what we'll do, we can mark it. So we have done this, use this filter design, and we have applied, and we have compared with different architectures, ZF methods. Okay, so and this paper is published in VLSI journal. So these are some applications we have seen. There are many applications we have done. Okay, so next we will go to the ASR system. What is my objective in ASR system? My objective is I have to remove the noise or the pitch variations. Okay. Basically, we are working for some period for a development of automatic speech recognition and a KWS system for children's speech. Okay. So there we can use this such a filter. We can design such a filter to remove the pitch effect. What is the pitch? Pitch is the high frequency variation in the data, as I told you. So that those high frequency signals I can remove from the spectral domain, from the spectrum. Okay, the magnitude spectrum. I can build a system which is equally work for adult and child. There is a many research on this topic for last 3-4 decades. Okay, so we have done something. Okay, so in ASR, as I told, we have a data, we have to do the feature extraction. Okay, then there is a lexicon dictionary, that means data translation. If you have observed this Cambridge dictionary and all, for every word there is a breaking of the used words, how we used to use the generate the phonemes, and there is a language model. Nowadays every time in TV you are observing large language model. This is the language model. Okay, initially we used to this the conditional probability and all to find out language model. Nowadays people have trained this language model using huge amount of the text data. So how the grammar rules, all those things, there it is. And the acoustic model. Acoustic model means we have two things. One is data. There we have extracted the feature, and we are decoding the data with a probability word. This sound in this given frame of data or spectrum or a feature, it corresponds to this sound in it. And this language model also correcting this thing. So there are two things. Okay, so that this is the basic block diagram of a ASR system. Nowadays people are saying this end-to-end system. That means this feature extraction we can directly do from the neural network. Okay. For that system, as I told, it requires a huge amount of data. If you have, this most important feature in the speech domain is the male frequency crystal coefficients. Or you can say log filter bank energy, or you can say whatever is variant. Okay, through LP analysis, all this LPCC, all those things. Okay. So what do we do? Given a speech, since speech is a non-stationary signal, we used to use this framing and windowing, 20 millisecond, 10 millisecond shift. Then we will apply the discrete Fourier transform. If I will not include this form, this block, just forget about something. Then we will apply the male filter bank, logarithmic, then DCT, then we will get the MSV. This is the pipeline for MSV. So now in a speech, where it will be most pitch affected? Most pitch affected in the vowel, because vowels are produced by the vocal fold vibration. Okay, and non-vowels are less affected. So I have an algorithm to find out the vowels and non-vowels. So now I can filter the vowel regions with a higher value of A. This filter order, if I put A is equal to 0.9, it is a very sharp cutoff filter. If I put 0.5, it will flatten. Okay, so we can apply to this. Okay, you can see we have a frame of data. There is a pitch variation. If I put A is equal to 1, it is just accumulated to add up. It has no information. If I put some 0.995, I'll have some structure. If I put 0.9, 0.85, you can see here there is a high frequency variation. We have removed the high frequency variation, only capture the spectral envelope signal, and that is informative. This pitch is a speaker specific factor that should be removed for development of a system. And we observe that it gives very good result, and we have published it. We have seen this for a child between this high this variation reduce. Okay. In a data, the training data should be matched to the test data. Okay, due to pitch and all, it is not matching, so we have to remove it. Okay. So this we have, I think we have published in InterSpeech. So next, we have designed this filter for further. Why not I model this thing, this data adaptive means this A value we are fixing 0.9, 0.95, 0.6 manually. Why not I collect from the data, depending on the data frame, the value of A will be automatically changed. Okay. If you look into my second slide, I have shown this for vowels. This first frequency amplitude is high, lower frequency is low. For consonant, first is low. At the high frequency, it is amplitude is high. So what I have to do? I have to remove the pitch from the vowels. So what I have to do? I have to consider the amplitude at this point, low frequency region. Okay. So what I'll do? I'll design a filter to do such things. Okay. This is the filter design. We have computed the DFT. Select the bins in the lower frequency range. Apply this accumulator 2 times. Get a value. That means what is the magnitude value? Beta. Then this beta will adaptively change for each spectrum. Okay. So it will come into back to that spectrum and divide by 1 minus alpha. Because why am I multiplying alpha? I will not allow this beta to go beyond 1. If it will go beyond 1, this is an unstable filter. Then this is the pipeline for MFCC feature computation. Okay. So if you look into, okay, this is the mathematics we have already discussed. This second filter and all, you can link it. Beta I, so we have to normalize it. And alpha. This is a adaptive filter because beta I is computed adaptively. Okay. So we can see these beta values for different sound unit, it is changing differently, adaptive manner. I need not to fix 0.5, 0.8. This A value will be adaptively computed from the data. This is adaptive filter, low pass filter. Okay, there are adaptive filter means the filter coefficient will change depending on the data. It is an intelligent filter. But it's a conventional filter, I have to fix the coefficient, the root I have to fix. Okay. So in adaptive filter, we need not to fix the coefficient. It will be changed depending on data. Where it is required, it will be high. Where it is not required, it will be low. Okay. If it is low, so this is a unvoiced, it will not filter it. If it is high, this is a vowel, it will filter it high frequency. Okay. So we can see same thing. Okay, we can get the spectrum but in an adaptive manner. I cannot fix this filter value. That beta will decide where I will filter or where I will not filter. Okay, so this is the thing. We can see we have, there is a 2 speech frames. Here it is around 200 hertz fundamental frequency. Here it is 100 hertz. If I develop a system on this data and test on this system, it will not work. So what I'll do, I have to remove the pitch effect. Applying my filter. If I'll apply it, you can see both the things, both the pitch values, high frequency, the pitch is removed. And how will you do it? If you know this overlap and add method, I'll go to the frequency domain. I'll apply filtering to the spectrum. Then again, I will, through inverse Fourier transform, I can come back to my time domain. Okay. So this is the thing we have seen analyzing. Okay, this glottal closure. Okay, initially see there is less very fast glottal closure because it's high frequency. Okay, glottal closure, the pitch is the interval, time interval between two glottal closures. Okay, I have a very small mass like a female, like a child, it will vibrate at a higher rate. Okay, but if I have a higher mass, it will vibrate with a lower rate. Okay, so this pitch and all. Okay, so we have developed and we have seen, observed this. Further, it is reduced this variation, and we have applied to different. Okay, and this filtering also, we know filter also remove the noise. Okay, we can see This is a noise fluctuation. If I apply this filter, it will remove this noise fluctuations. Noise fluctuations also. Noise means that is a variation in the amplitude. So it will observe in the frequency domain. So if I apply the filter, it will also remove the noise. So then we have developed this noise spectrum. You can see this is the original spectrum. If you look into the noise spectrum, noise energy is distributed. Okay, so if I apply this filter, it will not disturb the original filter, but it will remove the noise. Okay? So this works we have published in this pattern recognition and all. Okay, 2 papers. So we have done many things. Okay, I have just give a view. It is not like that a very big neural network can work. Okay, but a very small fundamental concept can work. Okay, if you visit a doctor, the doctor who is unexperienced, he used to give many medicines. But if you go to a doctor who can diagnose, he can, a small medicine can solve the problem. So these are the fundamental research, because this concept of speech, how it is produced and all, how with a small thing we can solve. Well, we have done many works on this, designing this filter and all. Around some 10-20 papers we have published. Okay, so you can see this is a very fundamental third semester thing. Okay. Some related publications. Most of the work is done by Professor Yegananda and our group. Okay, so you can see. I'll rest here. Okay, so you can ask me some questions so that we can discuss for 10-15 minutes. Okay. I have not shown this result and all because it is immaterial. You can develop any system. Okay, it is not like that you will use a simple system, it will be something. If you go to a bigger system, accordingly it will improve. Okay, you can ask me something so that we can discuss. This is a very fundamental concept. Okay. Hello.
Gayadathan.
I'll rest here. Okay, they can ask something. Okay.
If let me unmute them. If anybody having question, you can unmute the microphone.
Okay, just I have discussed this very small filter. How can it be?
Many students having questions from where they will start. Whether what are the basics required if someone wants to start working on speech processing or speech signal. So from where they will start? Many students having the questions.
If they want to start, they say, start from the speech brain, Python coding. Okay, because nowadays if you don't have any fundamental knowledge, you cannot work on this type of thing. Okay, so you can just start from a pre-trained model. Okay, and develop some applications. Okay, many codes are freely available in the speech brain if you are a computer science background people. Okay,
yes, so many of them are computer science background people, but
because they cannot cope up with such a research. They can just take the pre-trained model. Okay, just Web2Vec, OLM, start building the system. Okay, then if you are computer science background, you can change this neural network architecture. Okay, one way, or you can even pre-trained model, you can tune it. Okay, you remove some layer, you train with your model, or what are the pre-trained output, you apply filtering, all those things to that. It can be work also. I'm working now on that. This is my, since Jagabandhu told me to give some fundamental things, I told. But nowadays we are working like that.
Okay, so fundamental things are required. They have to.
Every research means academic means that is a fundamental.
Yes, without fundamental, like, yes, definitely.
But at least you should know what is speech and all. Because if you observe, those machine learning people, they used to work with the image because there is no fundamental knowledge required there.
Yes,
Just
sir.
image just give you the image, but speech is a high reach of information, and that you should have some fundamental knowledge, how is produced, what I have to change the parameters so that this feature can capture.
Yes, sir. So any questions from student side? Yeah.
You can start. Suppose let's say you are developing a emotion recognition system. In speech when side it is a emotion recognition system code is given. You take it and you plug it. You'll get some paper. Okay. Nowadays people are doing like that because this fundamental concept you can observe that most of the new group they are producing paper because they quickly club this Python code and all they can produce some result. But these old groups we don't want to do like that. Okay.
Yes, sir. Any question from student side? You can unmute and you can ask the question to sir. Usman, you have any question? I don't think so. So anyone want to ask something to sir?
Okay, then sir, we'll rest here. Okay.
Okay, sir.
We'll meet this time. Okay. Well, I'll go to come to Bhubaneswar.
Okay, okay. Thank you, sir.
Thank you. Thank you.
Thank you.